There lies a big challenge in making the aerospace field more sustainable. Clean Sky 2 has been initiated to encourage cleaner transport technologies, which reduce CO2 by increasing fuel efficiency, reduce NOx emission, and reduce noise emissions.
High aspect ratio wings can be a key contributor to significantly reducing the environmental footprint, aiming for fuel burn reduction thanks to reduced aerodynamic drag, while the wing weight penalty needs to be minimized. Key enablers to achieve this objective are the development of multifunctional and multi-purpose movables to support these functions.
The Manta project aims at developing novel wing movables to make the wing aerodynamically more efficient and lighter. This will reduce fuel consumption and, very important, reduce greenhouse gas emissions.
These newly developed technologies within Project Manta are expected to accelerate reaching the ACARE SRIA goals.
ASCO, GK & Fokker, the German Aerospace Center, the Netherlands Aerospace Center, and the Delft University of Technology closely collaborated to develop these novel movables. And aircraft manufacturers Airbus, Dassault, and Saab acted as topic managers and advisors.
One of the challenges during the design is the integration of these movables into a highly constrained space that is available in these lander wings. New materials, integrated systems of sensors, novel kinematics of trailing edge devices, and a design for flight radius number are key technology bricks that enable these concepts.
The development of these novel wing movables happened into 4 phases. The first phase is generating several multifunctional movable concepts. In the second phase, these concepts are explored in more detail. Parameters such as loads, weight, lift, drag and flight handling are assessed on the aircraft level. When all the required information is known, a down selection is made by the Manta partners. The final phase, the fourth phase, is the maturation of the selected concepts to technology readiness level 4 or 5. Large-scale demonstrators are designed, built and tested to demonstrate the feasibility of the concepts under realistic loading conditions.
3 demonstrators were down-selected: the winglet morphing tab, the multifunctional flap, and the pressure cell actuated flap. Later in the process, another promising concept was also investigated numerically in Manta, a morphing plate that can seamlessly adapt its shape to open and close the air inlet at the bottom of the fuselage. A concept which lends itself for use in especially confined spaces is that of fluid-actuated morphing unit structures, as they are the structure as well as the actuator in the setup. They consist of stiffening structures in combination with the elastomeric material to deform under inner pressure. Needed hydraulic aggregates, including control, can be placed locally near the wingtip, minimizing additional weight. Experimental results show that the use of pressure cells is a viable concept for future morphing systems.
We have been studying the ram air inlet flap, an inlet present at the lower part of the fuselage of various commercial aircraft. The flap is a mechanism that can be adjusted to control the flow of ambient air depending on the flight conditions. This flap typically consists of 2 stiff plates, but there is potential for weight reduction and improvement of aerodynamics if these plates are replaced with a single morphing composite flap. We developed different numerical methods to calculate the deformations of the flap under aerodynamic loads. And we also investigated how we should design the laminate such that the flap achieves the right shape at the right flight condition. With the help of our partners at GK & Fokker, we designed a flexible composite plate of varying thickness that can replace the original stiff flap, making it lighter while ensuring the high-quality aerodynamic flow without compromising its functionalities.
A preliminary design of the air inlet flap is tested to see whether it would indeed deform as expected and whether fatigue issues would arise. The tests were successful and demonstrated that a composite air inlet flap is indeed feasible. The morphing winglet tab is designed for a large passenger jet, and its goal is to actively change the shape of a winglet. movables such as ailerons and flaps are attached to wing structures by bearing-mounted hardpoints. This requires slots between the movables and wing structures to allow rotational deployment. These slots cause disrupted airflow, causing vortices or airflow separation, resulting in drag.
The morphing concept improves the lift side of the airflow by closing the upper skin and enabling morphing through a flexible zone. Flexible shear elements follow the deformation of the flexible part of the skin and transmit the air loads and imposed deformations.
The challenge is to achieve the correct fatigue life of the thermoplastic building blocks due to the varying out-of-plane loads in combination with, for aircraft construction, unusual, large out-of-plane deformations. The flexible shear elements require minimization of strains occurring from simultaneous bending and shear loading. For this, correct geometry and amounts of the flexible elements are important. Simulation helps to match these parameters for both skin and flexible shear elements to the aircraft program.
To demonstrate and validate the morphing concept in a realistic environment, use is made of hydraulic actuators for the application of winglet bending and tap deployments. Air loads are simulated by springs connected to the specific interface locations on the winglet tap demonstrator, generating loads that are proportional to the tap deployment angles. A digital image correlation system is used to measure and record data on the skin curvature. This facilitates the calibration of the theoretical morphing behavior model at Fokker.
A novel flap kinematics concept is developed by ASCO, combining high lift and aileron functionalities in one control surface. Today, these functions are ensured by two separate control surfaces. The flap allows the aircraft to take off and land at low speeds, while the aileron is used to perform the roll maneuver. The span of the multifunctional flap is larger than a traditional flap. It is supported by 3 stations and is moved forward and aft by 2 actuators. Additional hydraulic actuators, 1 at each station, ensure the rotation of the flap.
On traditional state-of-the-art trailing edge, the kinematics is based on a moving carriage combined with a rotating rear link. The rear link has a fixed length and is on one side connected to the end of the flap and on the other side to a fixed point on the support structure. In the proposed Manta multifunctional flap mechanism, however, this rear link is replaced by an actuator being able to change in length. It is now connected to the carriage and not to the support structure anymore.
As the actuator moves together with the carriage and the flap, one of the challenges is the flexible tubing. Tests have shown that the flexible tubing is able to foresee the necessary pressure to the moving actuator in different conditions throughout the complete life of the aircraft. NLR plays an important role in conducting the demonstrator test. 18 different settings and conditions have been tested under aero loads. Also, wing bending is included. The flap is then rotated, first at a slow speed, but then gradually increased up to 60 degrees per second.
The challenge lies in achieving a high flap rotation speed of 60 degrees per second, along with significant wing bending and air loads. To comply with this requirement, the test rig has been strengthened and high-flow oil manifolds, along with pressure reservoir buffers, have been incorporated. This ensures there's enough hydraulic oil and sufficient pressure to support the high rotation speeds of the flap under loads.
Within Manta, the multifunctional flap mechanism has reached a technology readiness level 5. The results are promising so far, but further technology maturation is still required. This includes additional testing in realistic conditions, but also the integration of the multifunctional flap mechanism in the wing needs to be further studied. An application to large passenger aircraft will also be part of this investigation.
After 7 years of intensive collaboration, the Manta project successfully concluded in 2024, pushing the boundaries of what's possible in aircraft wing movables. Beyond its remarkable scientific and engineering achievements, Manta opened new pathways for the development and maturation of ultra-efficient wing technologies and fostered exciting new collaborations. Its legacy will continue to shape the journey toward more sustainable commercial aviation.